What's up? Today we are going to talk about inverse functions. I'm super excited to talk about inverse functions with you guys. This is leading up to one of my absolute favorite things that we're going to talk about in Algebra 2. So I am totally stoked. So two functions, f and g, are considered inverses if the following is true. So if f of g of x, so we compose them, if that's equal to x, f of x, so if we compose them in the other direction, is also equal to x. So this is great because we can use the algebra here to be able to prove if two functions are what we are going to call inverses. Now, this is all like fine and dandy, but how do I know like what's going on there? So how do I know what an inverse actually is? Like, let's go ahead, see this in action, and we'll see if we can start to figure out what's going on with these inverses. So, steps for proving two functions are inverses algebraically. Very first thing we're gonna do is compose. Okay, so we're gonna compose f of g of x, simplifying one step at a time, folks. I know that sometimes my students get really cancellation happy and they just start crossing things out, but we have to be mindful of the order of operations as we're working. Then we are going to compose again, but this time in the opposite direction. So g of x, just like we did above, keeping in mind the order of operations. Um, then if we find out, right, that I'm going to list the other notation this time, f of g of x is equal to f here, g of x is equal to x. And we can say these guys are inverses. Alright, so the reason I'm starting with this is because this here is the definition of what an inverse is, right? That when you compose them together, everything cancels out and we're left with x. So what's going on here is I always, since we have to compose in both directions, split my workspace into two. And first, we're going to do f of g of x. So f of x. So in place of x in my function f, I'm going to plug g. So I always like to write it this way with a big open set of parentheses where I'm going to be substituting that whole function in for what used to be x. So the x one over 3. So that's my function g. Simplifying. So following order of operations here, I know I have to take care of this multiplication first. Well, 3 times this, dividing 3, those 3's are going to cancel, and so I'll end up with x plus 1, and then this is minus 1. Well, plus 1 and minus 1, those are going to be a zero pair. That's going to cancel, and we're ending up with just x. So what happened here was the operations of f, we're able to undo the operations happening in g, and we ended up with just x. Pretty cool. All right, next, we're going to go the opposite direction. So we're going to take g of f of x. So my function g used to be x plus 1. Again, I use big parentheses to put a whole function in there. Quantity all over 3. So my function f is this guy here, 3x minus 1. All right, so I know last time the first thing we canceled out was multiplying and dividing by 3, but we can't do that yet because not everything is being multiplied by 3 up top. So what we do here is actually the opposite. See how these ones are going to cancel first. x over 3. And now those 3's will cancel, and I end up with x. And so now we're able to say, therefore, this is a really cool symbol in math that we can use to write the word therefore, since there's so many letters, the word therefore. So therefore, they are inverses. You draw your conclusion at the end, because I asked you to verify whether or not they are inverses, and even if I had showed that when I composed in both directions, I ended up with just x, I haven't told my teacher or whoever's reading my work quite yet what that means in terms of the problem, so you got to have your little conclusion there at the end. All right. So in inverse, what we see here is that we've got two functions who contain inverse operations, but not just all the inverse operations. They're in like the reverse order too. So notice how in f of x, my inputs get multiplied by 3 and then we subtract 1. But the opposite order happens in g, not as well as the opposite operation, because we have, or the inverse operation, because when I plug something in for x, first we add 1 to it, and then we divide by 3. So pretty cool stuff going on here. Now we're going to consider two functions, f of x and g of x. We're going to graph each function on a coordinate plane below and see what we notice. All right, so first, let's call this one f of x. We'll graph in blue, and g of x we'll graph in blue. All right, so f of x is a cubic that's moved down 2 spots. So I know kind of its middle point is here, negative at 0, -2. Okay, and then draw a couple more points. So, because we know in a cubic, from that middle point, it goes over 1, up 1, since that's 1 cubed, and then over 2, up 8, because that's 2 cubed. That horizontal distance we traveled cubed, which is pretty cool. So I'm just going to connect our dots. Right. Out there. All right. Now let's go to the cube roots. So g of x is a cube root graph, and it has moved left 2 units. So it's got this here, and it goes up 1 over 1, up 2 over 8. So to connect this dots. And it's kind of like a cute image. I don't know. This is my idea of art, I guess. But what I want you to see is if I were to draw in dotted line here at y equals x, just the parent linear function, maybe you can see it better if you sort of turn your paper or your iPad or whatever you're typing on or writing on to look kind of straight down that line. I can see that these are mirror images of one another. If I kind of folded this paper on that dotted line, they are reflections of one another, which is really cool how that happened correctly, because we know here that this cube root and a cubic, those are inverse operations, right? Cubing and cube rooting. But here we can see moving down 2 and moving left 2, how that interacts here as well. So what did we just discover? We discovered the functions f and g are reflections of one another about this is called the ideal line. because whatever you plug in is what you get out. You get it itself, right? So it is considered an identity. Alrighty. Graphing. So we're going to use something called the horizontal line test. So to talk about functions. So previously we used the vertical line test. If you've been sticking with what we have on functions, vertical line test was used to determine whether a relation was a function. Since inverses are reflections of one another about that line y equals x, we can use this reflection of a vertical line about that line, which would be a horizontal line. Use a horizontal line test to test whether the inverse of a function is also going to be a function. So this is important. Every relation has an inverse, but not every inverse is going to also be a function. So that's what we're concerned with here with the horizontal line test, is not whether the inverse exists, because it does, but whether it is a function. So if you have a function and it passes both that vertical line test and the horizontal line, BLT and HLT, then this function is considered 1 to 1. So that means each input goes to one output and each output goes to exactly one input. So we're going to look at this example here and think about this horizontal line test. So if I were to draw a horizontal line across my graph, technology is so cool because I just drew a really ugly line and then it made it look pretty for me. All right, and I were to grab that line and sort of move it up and down, then 1 points on the line. So we say that this passes the vertical line or the horizontal line test. All right, and so it means it must be a function. So another thing that's cool here is this is a linear function that we have to graph, and the inverse of a linear function is a linear function. Pretty cool. And so, because they're both functions, the original and its inverse, because it passes the HLT and the VLT, we know it is 1 to 1 as well. Next, you may remember going the for 1, but if not, you'll see them again in a little bit here in Algebra 2. This is an exponential function. And so you might be thinking, it's going to fail the horizontal line test right here. But actually what's happening is there's a horizontal asymptote there, and it's getting closer and closer and closer to 0, but it isn't actually touching 0 at any point. And so it's just getting exponentially closer to it. And so this is now going to fail the vertical line test, or the horizontal line test. This as a function, because it's past the vertical line test, you may be thinking, I don't know what the inverse of a exponential function is. And you're right, that's my favorite thing that we're going to talk about in the next chapter. So I wrote past this VLT and I meant HLT. So try to write in the highlighter. Guys, who let me be a teacher today? I'm messing up left and right. All right, horizontal. All right, that's all better. Last but not least, we notice, oh no, this quadratic, y'all, it's not passing. But you can see for the majority of the time, except for at that vertex, it is constantly crossing my horizontal line in 2 spots. So that means that the inverse of a quadratic is not going to be a function. Oh no. Alright. So how do we go about finding the inverse of a function then? inverse. So first is if it's written with function notation, we want to remove that. So we're going to replace, so we're going to swap or switch, but I feel like swap is more fun to say, x and y. Solve for y. And then if f of x passes that horizontal line test, then we can replace y with notation for the inverse, and we say f inverse of x. So here we're looking for the inverse of this linear function, f of x equals negative 1/3 x minus 4. So I'm going to replace that with y. So I'll have y equals 1/3 x minus 4. And what we're doing is we're like manually reflecting over that line. This is good. For y. Sides, log x plus 4 equals negative 1/3 y. That negative 1/3, I'm going to multiply both sides by 3. Notation, so functions are used in inverse is equal to negative 3 go ahead and box that up. That looks super nice. We want to go back to the quadratic because I know what you're thinking. Um, we know what the inverse of that is. It's a square root function. We already studied it earlier this chapter. Well, remember, the square root function looked kind of funny, like half the sideways parabola, and here's why. So if a function fails that horizontal line test, we can restrict to non-negative plus 0, only non-negative real numbers, so that the inverse is a function. Deal is find the inverse here of this quadratic that's restricted. So first I want to talk about what this looks like here. So if I've got f of x is equal to x squared plus 3, but x is only greater than or equal to 0, that means I only want the non-negative part of this. So x squared plus 3 is quadratic that's been moved up 3 units, and so its vertex is going to be here. 3, but I'm not going to plot any points to the left of that vertex. I'm only going to plot points to the, so it goes over 1 up 1, over 2 up 4. A parabola. Inverse. So first we're going to replace f of x with y. So y equals x squared minus 3. So 2 is going to swap x and y. So x is equal to y squared plus 3. Right, so we take 3 away from the sides with x minus 3 equals squared. Sides, but because we restricted the domain of the the domain of the original, we only have a positive root here. We don't want to use the negative, and so here we're going to not use the roots, and so we're going to have y equals the square root of x minus 3. As we restricted this, we said, hey, this is going to be able to be a function, so we're going to call it f inverse of x is equals. Go ahead and graph this guy. So, sure amount, right? All right, there we go. So, this is a square function. X minus 3 means it's moved right 3. So, kind of its ending point is right here. To go back, any line here. Y equals X. Learning a little bit about inverses today, y'all.